Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Fortran programming, and if you guys were able to manage yourself and come to this point, then congratulations, you have successfully mastered the basics and the most vital parts of Fortran programming. Now the good news is that whatever you learned so far will be more than sufficient for you to handle a wide variety of programs and wide variety of applications. Okay, this is actually the last video in this tutorial series, whereas I have some more tutorial series to go on that will come in some more time. And before that, I thought of giving you guys a little introduction to what can be done if you guys have if you reasonably mastered Fortran. Okay, now this is more of what to do and where to go from here. Alright, now to give you guys an overview, we'll be looking at other Fortran compilers, some comments about C and C++ language, some parallel computing procedures like OpenMP, MPI, some mathematical computing packages and languages which are free and paid, and some details regarding interpreted languages like Python, R, some other packages like other programming languages and packages like NCL, Ferret, Graz, and other tools like Maya, VI, Paraview, UVCDAT, etc. Okay, don't get frightened by this entire stuff, but we'll not be going detail into it. Just a little touch. I'll be just touching upon here and there and stuff. Touching upon here and there with a little information. Okay, as far as other compilers are concerned, if you guys remember my first two videos, okay, first two videos in the introduction, I mentioned that there are several other Fortran compilers other than GNU Fortran. We are using GNU Fortran for our purposes in all these tutorials. There are other Fortran compilers like Intel, NAG, Cray, PGI, and many others. Okay, the reason why people prefer these is because they have certain non-standard features that make certain other processes simple, and these compilers can take the advantage that is present in certain system architectures. Okay, these compilers, if you guys notice, most of them are supercomputer manufacturers, even computer manufacturers. Intel is specifically a processor manufacturer, microprocessor manufacturer, so they know how the systems and processors kind of work. So using that, they can optimize certain code, make certain codes that take the advantage of the system architecture to make the optimizations faster and all, and they have large amount of features as well. And these compilers are extremely good for doing parallel programming. For serial programming they might be good, but for parallel programming they're extremely good. And if you want to interface these compilers, these Fortran compiler language Fortran files with other files like C or C++ and all, they are very good, but provided they have to be in the same thread. For instance, if you are having Intel Fortran, it compiles and merges with C files and C++ files very nicely, but provided those two C written in, so use C compiler, Intel C compilers, Intel C++ compilers for the same. And whenever you get compilers like these, like Fortran from compilers like these from Intel, Cray or PGI, they come along with debuggers, profilers, etc., and several other features, and they also come along with parallel programming definitions inbuilt into them. But they come both at free as well as they come in two categories. Some of them come under free category, some of them come under price category, and that depends on which one to choose. That is depend on your needs. And these compilers are recommended specifically for intense computation jobs that demand supercomputers or workstations. For normal jobs like this which we have done here, we don't need any of these. But if you want to do a very large simulations, like a two-dimensional calculus simulation, or wherein you have to generate run any atmospheric model or some quantum mechanics model wherein you're calculating the turbulence in fluids, or how certain waves propagate in atmosphere, or how gravity anomalies interact. I'm just making up stuff, but this, I think you get the point. Wherever in places where you have to do a very large set of sentence calculations and all, these compilers are very much preferred. All right. And now regarding C and C++ languages, these two are actually these are much more superior compiled programming languages. They came little later than Fortran. See, Fortran has its own limitations, in the sense you cannot use it in you can use it for general purpose applications. So I mean, maybe if you have some other program that does all the main front end job, and if you has a number crunching business and other related stuff that you have to do at the background, Fortran can be used accordingly. But if you want to do a very fancy processes like building a lot of applications solely from Fortran and other stuff, and for example like making memory making operating systems and stuff and other stuff and all, Fortran will not work. Rather, C and C++ are superior in that process, wherein you can do a lot of stuff with that. Well, C and C++ does not have any array slicing features like that of Fortran, but that's kind of a little thing, but that doesn't matter actually. That is not a big feature to be worried about, but it has almost all the features of Fortran and more features that are actually absent in Fortran. So these make certain jobs much easier and even more interesting in Fortran. And if you ask me which one to choose, okay, I leave it to your personal choice. If you guys are extremely good in C, you guys C or C++, you can go ahead with it. And if you guys are okay with Fortran, well, I won't mind either. Go ahead with Fortran. Both of them are equally good with respect to scientific computing. For if you want to use some language that is generic and can be used for multiple applications and all, other than Fortran, then C, C++ are the better choices. So that's why I'm mentioning here which to choose. It's based on personal preference and based on your application. And regarding for parallel computing, there's something you have to keep in mind. Okay, whenever you run a program, okay, it just runs in a single core or a single processor, okay, and it runs serially, in the sense one instruction followed by the other and all. Okay, now this paradigm is very good, but if you want to make if you want to get your job done much faster and all, and much faster and all, then what you have to do is that you can make multiple cores in a system work simultaneously. Now if you guys I'll just tell you guys give you guys an explanation as to what I mean here. Okay, this is my system monitor, okay, for my Ubuntu, and my laptop is an i7. I'm running this in my laptop, which is like an i7 third generation. Okay, it is a quad core processor, and if you guys know, quad core processor, and each of the 4 cores have two hardware threads. So if you guys notice, it's like for my laptop is like one single computer with 8 individual independent processors, okay, all sharing the same RAM. My system has about 8 GB of RAM and 8 processors, 8 threads. So what this says is that simultaneously 8 jobs can be run in my system. And if you guys notice these color lines here, these are indicating how much lower load capacity is there on each processor, and each thread. These are actually colored. Now, and as of now, each of these threads, they are actually working on certain program. Now, if you guys want to look at what are the other programs that are being available, this is my processor thread. Okay, if you guys notice, there are just so many processes that are running on the background, each consuming its own set of memory over here. Now processor, what it does is that they just split all the jobs among all the CPU threads, and each CPU thread will do some job and all. okay, and your RAM is actually used for storing all the memory that is required for running these processes, and all. Now imagine if you run a program, okay, at any instant, like any instant as of now, what it will do, just only one of these 8 CPUs in my system will be active, will be running the entire stuff. But what if uh, you write your program in such a manner that all your you can call multiple of these threads, like two of these, or 4 or 6 or even 8 of these, to run simultaneously the same program. Well, is it possible? Yes, it's very much possible. And for that to happen, uh, for that to happen you need a different paradigm of programming language or a principle, and that is called as parallel computing. What it does is that it makes the use of multiple cores or multiple processors simultaneously by splitting the job among these cores. Okay, now there are actually two kinds of ways or procedures to make that possible. One is an OpenMP procedure, and the other is an MPI procedure. OpenMP procedure, okay, which is OpenMP, in short, which actually stands for Open Specifications for Multiprocessing. Some people might call it open for multiprocessing. Doesn't matter, but okay, this is used for computers having shared memory, like your laptop or a desktop, wherein all your processors are in the same motherboard and they access the same RAM associated with the motherboard and all. Okay, for those computers and all, OpenMP is very good. MPI is an entirely different paradigm, entirely different paradigm of parallel computing, wherein, okay, it stands for multiprocessing message passing interface. MPI is entirely different, wherein it can be used for shared or distributed memory. What it does is that the same program is being run in all the set of cores simultaneously, and these cores need not have the access to the same memory. They can have independent memory allocations or the different memory allocations and all. Okay, and all the cores will be running simultaneously in all the processors, and each core will be doing certain bits and pieces of job. Okay, suppose there are like n tasks in a program. Okay, this program will be running in all the processors, and each processor will do a certain bit associated with it. Now this kind of programming interface, parallel programming algorithm or principle, okay, is actually used for supercomputers very much. And there are some methods wherein there are some procedures wherein you can use OpenMP and MPI in parallel, but I'm not sure as to how. I heard that there are processes, but I might be wrong. But I heard that there are procedures to combine these two procedures, run simultaneously. Okay, and these are actually functions, subroutines, directives, and all. These are actually functions, derivatives, and subroutines that actually work on top of a compiled language. Okay, these two do not work separately. Rather these are just like additional features to programming languages like C, C++, or Fortran. So the thing is, your program can have these commands built into them, and and these are like additional libraries or subroutines to C, C++, Fortran to make the job done. And other than that, these are not the only technologies available. There are other features like OpenCL, OpenCC, and all, OpenACC, and all. I think which kind of does a similar jobs like OpenMP or MPI, but that depends on the hardware manufacturers. Some people are also using graphical processing units, literally a graphic card, for doing parallel computing and all, which is actually rapidly emerging field. And some people use something called as OpenGL, and this is mostly for graphics related jobs, but this also comes in a parallel computing, but in a different domain. Okay, and so if you guys were trying to look at parallel computing and parallel programming and all, if you guys come across terms like OpenMP, MPI, OpenCL, ACC, OpenACC and all, now you will understand what exactly mean. Okay, this is the this is the skin depth explanations of it. There are a lot more stuff under the hood. And for people I mean, parallel computing is for those people who really want to do a very intense computation jobs and all. For students who just want to use uh, simple calculations and get some results quickly, there are a lot of mathematical packages available. I am classifying them under two categories, like paid category and free category. What I mean by paid category is that these packages are actually pay. These packages do not come as free, whereas you have to pay. You have to pay and get your own commercial license to use them. Some of them, and the most popular ones among them, are MATLAB, Mathematica, and Maple. Not in any order, but okay, not in any order. These are actually very common, to be honest. Okay, these are very good and they have very good packages, and they have a lot of extensive features, like you can do a lot of statistical job, integration, plotting, differentiation, interpolation. They have features for doing a lot of computations regarding aerospace, bioinformatics, blah blah blah. You can just go on. There are just lots and lots of features that are available: MATLAB, Mathematica, Maple, etc. Okay. Now these are like more like interpreted languages. Okay. Some of them are interpreted language like programs. Some of them are just command like ones. But that depends on the package that you're using. All right. Now, if you MATLAB is in specific is like an interpreted language, and these are working good. And there are free packages, mathematical packages like Scilab, Octave, FreeMat, and several other. There are several others also. These are actually newly emerging ones, and these are completely free. Some of them are software clones of them, of some packages on the top, like above. See, if you guys have licensed versions of these, if you want to get a proper licensed version, and that too maybe a full version or something of that sort, it's really expensive. Some of them can be really expensive, that it'll make it literally impossible for people to buy and use. Okay, but the features are really good. Okay, on the other hand, these programs like Scilab, Octave, and FreeMat, they are free of cost. And for many practical applications, you can if you have a good knowledge in any one of these programs, you can very well use them nicely without having having to use these. And I'm not saying anything bad about these packages, not saying good about. I'm just giving a comparison. Okay. Now many people are preferring to use use packages like these, because these are emerging, and a lot of features that were not available that were available in these packages, which are not available here, are emerging out. And these are also like interpreted language based packages, but these are very good. These are also very good to consider. And there's a reason why I prefer mathematical packages over mathematical packages, because these have a lot of features to process and operate on file systems much easily. Like if you want to access text files, read data from it, or if you want to access some little more complicated files like CSV files, or netcdf files, or hdf files, or excel files, and several other data files and all, these kind of packages can handle them very nicely. Whereas if you want to do the same job in Fortran or C or C++, then it will be really messy. And it will be a real headache. And besides, these packages have very nice plotting features that make your plotting and visualization stuff much easier. And as an extension to mathematical packages, there are other interpreting languages also. Actually, there are many. I'm just concentrating on only two of the languages which I've known so far. Okay, Python and R. I've used Python very extensively, but I haven't used R much. I haven't used R at all, but I have heard how R works and all. So I'll just explain these two. But I remind you, these are not the only interpreted languages available. There are several others that can be used. Okay. Now, Python is very easy to learn and it's very rapidly emerging in scientific computations, and it has a lot of programming. You can integrate several programming languages files into it to run them properly, and it has nice graphic options, and you can do a lot of job. With Python. Python can be not only used for scientific computation, you can use it as a general programming language for several other applications also. Whereas R is concerned, this is primarily used for statistical purposes. Okay, it produces very good quality of graphics, and many recommend R for its graphic plots and all, because the graphics, the images and produced by R, they're like really good. And R is actually preferred for data processing and data analysis, where you have a large chunks of data, and if you want to calculate you want to do some statistical calculations like the probable distribution functions, or testing of a hypothesis, curve fitting, linear interpolation, regradings, and several other stuff, wherein you need a lot of you're going to use a lot of statistics related jobs. Okay, R is very good for that. Okay, and I'm not sure how R can be used for general programming language, but general interpreted language, but it's really good in that regard. And finally, just to give a slight conclusion, okay, there are other packages that can be also considered. These four are actually meant for atmospheric and oceanic science students and researchers. I mean, those people who work with the studies of atmospheres and oceans and all. But I'm not restricting them alone to this, but you can several people can use them. Others also can use them. Some of them are NCL, Farad, GRADS, and UVCDAT and all. These are NCL, GRADS, and Farad and GRADS are very popular, and even UVCDAT is very popular. UVCDAT is more of a Python based. Application, wherein these have a lot of features that makes plotting easy, like latitude longitude plots. What else? Averagings, streamline functions, weighted averages, and all, polar and the latitude area corrections and stuff. These programs have those features to do. These are like interpreted programming languages also. And in UVCDAT, you can include Python scripts to do the job that you require also. Okay, and for people in general, okay, who want to use any visualization tools, okay, there are many options available like Visit, Paraview, Maya, VI, VTK, and several others. These are more of 2D and 3D visualization tools which can render good graphics and stuff, which you guys can consider working about. And these are not the only ones. There are many others too. And what will be a very interesting thing is that if you are able to combine these packages or these programming languages or these mathematical packages with Fortran, C, or C++. Okay, if you're able to combine these two in a proper manner, then you have the advantage of extremely fast data processing and fast arithmetic done by the compiled languages, and you have a extremely good extremely good plotting and data handling stuff features of interpreted languages. These interpreted languages and stuff have very good with respect to file handling and memory management and all. Okay, and you can make a lot of jobs easier. So if you were to set a trade-off, set a compromise by using, not a compromise, but if you make a proper merge by using one of these packages with interpreted languages or mathematical packages like these, any one of these with and if possible parallel computing with C or C++ or Fortran, then your job will be very nice. And finally, as a concluding part, I'm thinking of starting this new series these 6 series in the future. Okay, and I cannot promise you as to when it will come or whether this will come or not. This is just an ambitious target. I hope this will come in the future. Immediately I'll be starting a new series on advanced Fortran tutorials, and in these tutorials we'll be covering the remaining parts of Fortran, that we did not cover in the basic tutorials. Okay, and then in the future I'll be working with Fortran plus OpenMP, how to implement OpenMP stuff in Fortran and look at it. And then I'll jump into scientific Python. Now in this tutorial series, if I were to conduct, this will not be on basic Python programming language, because I just searched in the internet to see how many basic Python language programming languages contents are available, and to my I wasn't surprised. There are like tons and tons and tons of features available for basic programming. So I'll be just directly jumping into scientific programming, and this will be very much useful. And then as a later series, what I'll do is that I'll be combining Python and Fortran together for some applications, like if you had to solve certain linear advection equations or something, or solve some Ragikuta scheme for numerical methods or something of that sort, and we'll do a lot of job with that. To make that possible, I'll be using Python and Fortran together I'll let you guys know how to merge these two properly. And then in the possible tutorial series, I'll be explaining guys how to implement MPI procedures in Fortran. Now these are just proposals. I'm not sure. I'm not promising you that I'll put all these, but I'll do my best to put many of these stuff on the internet, any of this stuff in the next coming time. Okay. And with that, thank you guys for your patience, and thank you guys so much for all your efforts and for your help for watching my tutorials. I hope you guys learned a lot of things, and hope you guys learned a lot of stuff in Fortran. And to be honest, I'm really happy that I made this tutorial series. And to be honest, I learned a lot from Fortran that I haven't learned while learning on my own. While when I was teaching you guys, I was able to learn a lot, and that gave me a lot more reinforcement on the concept that I have. Okay, and hope you guys enjoyed this tutorial series, and thank you guys for watching. And if you guys are able to come all the way here, congratulations guys. Now you guys are really good in Fortran, and you can jump into any job, and your confidence will be very good in this process. Okay, thank you guys for watching. I'll see you guys in the next series, and take care.